What's up, everybody? It's Miles here from bootcamp.com, and today we're going to be covering the chest wall and lung curve. So before we go over this curve, let's just do a quick recap. So recall that our respiratory system consists of our lungs, and just outside of the lungs, we also have our pleura, and then outside of the pleura, we have our chest wall. And recall that the lungs always want to collapse inwards, and the chest wall always wants to expand outwards. And like we said, there's a tug-of-war match going on between the lungs and the chest wall, and they're both pulling, and in between them is the pleural space, and the pleural space is being expanded, and as it's being expanded, because it's a closed space, we are generating negative pressure within the pleural space. Okay, so our chest wall and lung curve is drawn on a graph that has an x-axis that consists of force and a y-axis that has volume. So in terms of volume, we start down here at residual volume, and then as we increase our volume, we eventually get to FRC. And can you remember what volume from our last video is between residual volume and FRC? That's right, it was the expiratory reserve volume. And as we expand our volume from FRC, we eventually get to total lung capacity. And can you remember what capacity is between FRC and total lung capacity? That's right, it was our inspiratory capacity. And so for our x-axis, the more we move right on the graph, we are increasing our collapsing force. And the more that we move left on the graph, we are increasing our expanding force. And so the first curve that we're going to be adding into the graph is going to be our chest wall curve as shown. So if we take a look at this curve and we look at this point down here at residual volume, recall that we said residual volume is the smallest volume the respiratory system can normally go. And at this volume, the chest wall is going to be very, very depressed. And so there's going to be a large drive for the chest wall to expand outwards. And so in this way, the chest wall is kind of like a spring, and residual volume is essentially we've compressed that spring all the way down to its shorter length. And so at this length, it's going to have the largest drive to spring outwards. And so as we increase the chest wall volume, we are letting it expand and having it let go of some of that expanding force until we actually reach total lung capacity, at which point the chest wall is actually a little bit stretched out. And so it's kind of like we took that spring and let it spring out to its normal length, and then we're actually stretching it a bit such that now it has a bit of collapsing force. So at total lung capacity, the chest wall actually has a little bit of collapsing force. And now we're going to add in the next curve, which is going to be the lungs as shown. So if we take a look at this curve and we look at this point all the way down here, recall that we can never actually reach this point because this is saying that we've exhaled our residual volume. But in some disease cases, such as pneumothorax, the lungs will actually completely collapse. But for the sake of physiology, what we're saying is that if the lungs were to be completely collapsed such that there was no residual volume in it, then there would be no collapsing force. But the moment that we start to increase the lung volume and allow it to expand, it will start to increase its collapsing force. So the more that the lung volume increases, the more that the lungs will want to collapse until we get to total lung capacity where the collapsing force in the lungs is at a maximum. And finally, remember that the chest wall and the lungs are connected to each other via the pleura. And so respiratory physiologists like to consider a curve that takes into account the chest wall lung system. So let's add in that curve here. And so the way to generate this curve is we're just adding the lungs and the chest wall curve together. So if we just arbitrarily assign collapsing force to be positive and the expanding force to be negative, if we were to take a look at, let's say, this volume right here, the lungs have this positive collapsing force and the chest wall has this negative expanding force. And if we were to add those two values together in our combined system, we would end up somewhere around here. And so the most important point on this graph and the most important point in this video is this point right here, right in the middle of the graph. So we can see that this point right here corresponds to a volume of FRC. And we can see that at FRC, there is a certain lung collapsing force, and there is also a certain chest wall expanding force. And on the combined chest wall lung curve, there is a force of exactly 0 because the lung collapsing force exactly equals the chest wall expanding force. And so that tug of war match that's going on between the expanding chest wall and the collapsing lungs is exactly equal and balanced at FRC. The expanding force of the chest exactly equals the collapsing force of the lungs. And so we don't need any musculature to maintain the respiratory system at this position. And so that's why we say that at FRC, it's at rest because the respiratory system is in balance. And so, like we just said, at FRC, lung collapse equals chest expansion. And one more point, and I've seen this on a boards question, is they like to ask, what's the pleural pressure at FRC? So even though at FRC the tug-of-war match is balanced, it's still a tug-of-war match. So we still have the chest wall expanding and the lungs collapsing. It's just that the pulling on both sides are equal, but we're still pulling on the pleural space. We're still expanding it. And because it's a closed space, that's going to generate negative pressure in the pleural space. And so remember we said at rest, the pleural pressure is about -5 centimeters H2O. And during inspiration, it's going to become more negative, and during forced expiration, the pleural pressure becomes positive. All right, and that's all we got for our video on the chest wall and lung curve.